Namaste. Welcome to this channel Dr.ARM's Chemistry. Friends, we were discussing electronic spectra in which we have seen the various aspects and the pre-ion term, etc. Today we will see the coupling of spin angular momenta. Coupling of spin angular momenta. So we have shown this here. Coupling of spin angular momenta. So here we have to remember that for a single electron, the spin of the electron is plus 1/2. For single electron, spin that is ms is plus 1/2 or minus 1/2, plus 1/2 or minus 1/2. But so in that case, means when there is only one electron present in the subshell of an atom, the electron is free and it has no interaction with other electrons, or there is no other electron to have any interaction with that electron, and therefore there is no need of, or there is no possibility of any interaction or this type of coupling of spin and angular momentum. So when we add, or when there are two or more electrons in the subshell, the spin of each electron, spin magnetic moment of each electron produces the magnetic field. So each electron will have its own magnetic field, and when these electrons are staying together in the given subshell, each magnetic field of each electron shows interaction with magnetic field produced by other electrons, and therefore there is coupling. Similarly, the coupling results in the total value, that is spin angular magnetic moment or quantum number. Here, in order to explain this coupling of the angular momentum of the electron with the magnetic spin momentum, this total spin of the electron with the total angular momentum of the electron undergoes coupling with each other, and that is shown by Russell-Saunder, and therefore it is also called Russell-Saunder coupling, or in simple words it is called LS coupling. Here, in order to explain this coupling, we need the ms values, that is spin magnetic moment values, and the spin angular momentum values, that is L values. So here we need the L and S values. We need these LS values in order to explain the behavior or interactions of the electrons with each other. So we can have the S values. We can have the S values plus 1/2 or minus 1/2, and we can have these L values starting from these L to L through 0 to minus L. So there is 0. So L to 0 to minus L. So in this way, the total angular magnetic moment is represented by L. The total spin angular momentum is represented by, a quantum number is represented by +1 or -1. Means this is actually the plus S. We have to here represent that this MS value is +1/2 or -1/2, and the S value, that is total spin angular momentum quantum number, E depends upon the total number of electrons present in it. So that is called the summation of MS, summation of SMS values. Therefore, similarly, we can have the ML values. So from this, we can get this L value as a sum of the ML values. Sum of all ML values. So for example, in case of this P2 configuration, we can have, or we are having, the subshell with these Px, Py and Pz orbitals, and these are having their ML values +1, 0 and -1. +1, 0 and -1. So depending upon the number of electrons present here. So if we are having, say, only one electron, it can be placed in any of these orbitals. But according to the rules, for distribution of electrons, we have to choose maximum value of ML for placing one electron. So the first electron should enter into these orbitals with maximum value of +1. So in these three orbitals, the maximum value is +1. So after putting the first electron, then we want to put one more electron. It should go with this 0 value, that is into Py, because it has to obey the Pauli's exclusion principle. Though second electron cannot enter into the same value, same Px here. So if we are having first electron, it should go into this Px. Second electron goes into this Py. But instead of putting this electron here, we cannot put the electron in the Px in order to avoid, or in order to obey the Pauli's exclusion principle, according to which no two electrons can have the opposite spins until all orbitals are singly occupied. Means every electron should have +1/2 spin, and for third or fourth electron we can put the electron with again maximum value. Means if we are having one electron here, second here, third here, then we can go to Px because it has maximum value. It cannot go here or here. But practically also, theoretically, all the orbitals are degenerate. So that electron is capable to enter into any orbital. But in order to obey the Pauli's exclusion principle, we have to follow the rules of distribution. So fourth electron will go here, fifth here, and sixth here. So in this way, the electron distribution will take place. So this is, so in this way, you have to choose maximum value of plus this ml. Similarly, we have to choose maximum value of this spin quantum number. So we know how to find out these values. For here, in this case, the ms value, then there are 6 electrons. The s value, that is total spin quantum number value, is sum of these is 0. Then L value for these is +1, 0, -1. So +1 and +1. There are 2 electrons. So +1, +1. +1, 1. For this 0, 0. For this -1, and for second -1. So this will give us total 0. This 1, 1 is cancelled by this 1, 1, 0, 0. So L becomes also 0 for such type of configuration. That is P6, for example. But when we want to put, say, 2 electrons, so for P2 configuration, we can have 2 electrons in this way with same spin but in different orbitals with choosing maximum ML value. Angular momentum value should be maximum. So in that case, so we can represent this type of distribution here we can show this in different way. So for this P2 configuration, we have here ms value plus 1/2. So this is shown with arrow, and another electron with, we are considering here only the spin, means ms values we are considering. So this another electron with ms minus plus 1/2, same spin. So in that case, we have to obtain the ls. So ls coupling means L plus S values gives us another quantum number G, that is Russell-Saunders. Cancel. So for this, the resultant for this is given as S, that is total. This is total spin magnetic value. So this is the sum of these 2 electrons, and that is 1. The sum is 1. Then if we consider another case, then it is ms. Then ms is, say, equal to plus 1/2, and it is having plus 1/2 spin, means in clockwise direction. Another electron has spin with opposite direction, and therefore it has ms value minus 1/2. So for such case, the resultant of this ms value is equal to S, and that is plus 1/2 and minus 1/2 each other. Plus 1/2 and minus 1/2. This is 2, and therefore we can get this S value. So this is total spin. And using this total spin, we can, so this S is used here. So this S is used here. Now, so this is about spin magnetic moment values. Then if we have, say, another electron, this type of configuration, that is P3 or D3. then we can have, that is configuration. Then we can have, there are 3 electrons, so these are 3 electrons with the same spin. So these electrons may be either in p or p-subshell. And for this case, this resultant these are ms values. So ms for this is plus 1 and, or we can say 3 by 2, because plus 1 half plus 1 half plus 1 half gives 3 by 2. So that is total ms, means this is s value. So ms for each electron is plus 1 half. This is plus 1 half and this is plus 1 half. So for here S is equal to 3 by 2. And when the electron is with opposite spin in electron, then we can have possibility like this. So there is 1 electron with, this is having ms value minus 1 half. This has plus 1 half. This has plus 1 half. So total the resultant is S is equal to 1 half. S is equal to 1 half. So the spin magnetic moment for, or total spin for this P3 or D3 is shown in this. Now we will see the LS coupling. LS coupling. So this is the Russell-Saunders or LS coupling. Now we will show this with suitable examples. Few examples. For example, if we consider this P2 configuration, then we can have the total S, that is total spin magnetic moment or quantum number value 1, and for M so for S is equal to 1, then for P2 configuration, or in short here we can represent like this. So there are other possibilities, that is distribution of this electron here or with opposite spins. So all these are considered here. So we can have, say, this electron and the energy associated with this arrow, that is vector, is considered in terms of h upon 2 pi. So that is, it is considered as h upon 2 pi. So that value is considered with the corresponding length of this arrow. When we are having the L value, when we have L value, then L is equal to 2. means here when we are having say possibility is there like this, at this L value, or here we can have this ML value. So this we have the plus 1 value, 0 and minus 1. So when the first electron has this value 1, and if we consider again one more electron there, so there are variety of possibilities. Then we can have this L is equal to 2. So here angular momentum has double the quantization compared to S is equal to 1 again. And from this we can get the resultant. We can get the resultant that is J equal to L plus S, and here L is 2, S is 1, so we get 3, and for here we will get this full, if we want to show full spectroscopic term, it is derived as the L value. Now we have to show here the L value equal to 0, then 1, 2, 3, 4, 5, etc. And for which the term symbol is equal to S, then P, then D, F, G and H, or for sixth it is K but not J. J is orbital. So using this we can have the spectroscopic term like this. On L is equal to 2 we have D, the term is D, and the spin multiplicity is, so we can calculate the spin multiplicity as 2s plus 1. So here S is 1, so 2 into 1 plus 1, that is 3, and here J is represented here, that is also 3. So it is read as triplet D, triplet D3, triplet D3. So this is read as triplet D3. Now for second possibility, when there is this L is equal to 2 and S is equal to 1. S is equal to 1. Then the resultant of this vector addition, that is J, is equal to this L plus, that is 2. That is J is equal to 2 because this is not taken here. So therefore, for this the term, spectroscopic term is the D with the spin state same, S is equal to 1, so 3, and here J is 2. So it is represented for a triplet D2. Now, for another case, we can have this same L is equal to 2 and S is equal to 1, and for this the resultant that is J is equal to 1, that is 2 minus 1, L plus, here it is, S is 1, but it is in opposite direction. Therefore, it is deducted from 2. So, it gives 1. And for L is equal to 2, the term symbol is same D. The spin multiplicity is 3, J value is 1. So we get this 3D1, that is triplet D1. And for another case, we can have this L is equal to 2 and S is equal to 0. So for this case, the term symbol resultant J is equal to is 2 plus 0 is equal to 2, and for L is equal to 2, the term symbol is same, that is D. The spin state is here, total spin is S0, that is 0. Therefore, the 2s plus 1 is 1 and J is 2. So it is called a singlet. It is called a singlet D2. So this is for this L is equal to 2, p orbital. If we take the p combination, p2 combination, then there are 2 electrons. So as we have discussed earlier, their ML values are plus 1, 0 and minus 1. So here maximum value, so if we keep the 2 electrons here, maybe in the opposite direction spin, so the maximum value of L is equal to 1 plus 1, that is 2. So for each combination, means we have possibilities of arrangement. That is, LS coupling is from 2 for each value of 2, 1 and 2. For S value 1 and 2. So we are having variety of combination. So we have seen the first type of D equal to 2. So first type of combination is C. Now we will see the second type of combination. So we have completed this combination. Then we will see for second, that is L is equal to, so we have seen this already. Now we will see for L is equal to 1, we will have this single arrow. For S is equal to 1, L is equal to 2. For here we are configuring this, L is equal to 1. In the previous section we have seen this maximum value 2. Therefore, this arrow was doubled. Now, the resultant is J is equal to, that is 1 plus 1, that is equal to 2. And the term symbol for 1, L is equal to 1 is P. So, the term symbol is P. Spin state for 1 is triplet. And J is 2. So, it is given by this 3P2. Then, when this vector is changing the direction, so the angular momentum, spin angular momentum is changing, it is shown in this way. That is, for L is equal to 1, this S is equal to 1 and this J is equal to 1. Therefore, we can have the resultant J is equal to this. J is equal to 1 we have shown. the term symbol is for L is equal to 1 same P state, the triplet, and this is for 1. The J value is 1. And now for another term, when this L is equal to 1, this S is equal to 1, then resultant J is equal to this 1 minus 1, that is 0. 1 minus 1, that is 0. So J value is 0. Therefore, term symbol arising is same P, because L is 1. So everywhere this term symbol P will remain same. Then this triplet is same because S is 1. Now J is 0. So it is read as triplet P 0. Now the 1 over combination is resulting in this way. Then L is equal to 1. L is equal to 1, and there is no S, that is S is equal to 0. And for this, the resultant is J is equal to 1, and therefore term symbol is same P, but spin is 0, so it gives singlet, and J is 1, so it gives P1 P1. The term symbol is 1 P1. Again, so this is for L is equal to 1. Now we will see third type of combination, that is for L is equal to 0. We can have this L is equal to 0, and therefore there is only S is equal to 1. And for this, the resultant combination is G is equal to 0 plus 1, that is 1, and for N is equal to the term symbol is S. So here term symbol is S for this coupling. The spin state is 1 means 3, and this J is 1. So we get this term symbol 3S1. Then for other type of combination, we can have L is equal to 0 and S is equal to 0. Means L is equal to 0, S is equal to, we have two combinations here. And therefore, we can have the resultant. J is equal to 0, and therefore term symbol for 0 is S. S for 0, the spin state is 1 and J is 0. So the term symbol, full spectroscopic, these are full spectroscopic term symbols. Spectroscopic term symbols. So we have shown such term symbols with its full form, that is full term symbol. So in this way, we can have the full term, we can in this way obtain full term symbols for this P2 configuration. Similarly, we can have also P2 configuration, D2 configuration, D3, D4, D5, etc. Or we can also show the term symbols for this P1, P2, P3, P4, P5, P6, or each type of configuration we can easily show the LS coupling. So we will stop our discussion. Thank you very much for watching it. Please subscribe to this channel if not yet, and press like button and bell icon. Thank you very much.